second class real-time systems. So you're still here, so you have not been scared enough yesterday by the English lessons. Hopefully you will stand until the end. So if you recall, yesterday we introduced the need for real-time systems, yet we did not finish explaining what happens in a real industrial environment, in a real automotive setting. So I took as an example yesterday the way typical things are done in industry. So you have a control guy that develops some nice and fancy control theory, and that theory needs to be implemented by us, by the developer, by the programmers on a real system. So taking an existing embedded controller, writing code, C code, AutoSAR compliant, whatsoever, and running in real time on the architecture. The control guy assumes that everything is infinite, everything works perfectly, that every response is immediate, but the actual reality is not the case. So we have a limited amount of resources, limited memory, the processors are slow, they need to consume not much power, and so on. So the example I started taking yesterday was the inverted pendulum. So you need to maintain the stability of the stick, and you basically enforce some action here, okay, to the pendulum, as long as you notice that the angle of the stick is positive or negative, okay? So it's a very simple, probably the simplest control loop possible, in which you basically read and enforce, read and enforce, okay? So this is the reading task. This is the basic computation with respect to the reference angle, the target reference angle that you have, okay, to compute it. This is the K is the gain, so how stronger should be the action with relation to the measured displacement with relation to the considered angle, okay? And you basically enforce that force on the vehicle, okay? So reading the angle, computing the displacement with relation to the target angle, such a displacement will be proportional to the output, to the force that you put on the car, okay, here, on the trolley, right? So this is a basic control loop, but yesterday we ended up trying to understand what is the reason why having a waiting synchronization event at the end of this iterative loop. The reason was, okay, we can perfectly leave taking this out, but the outcome would be to have the control task continuously executing, okay? Having a control task monopolizing the processing power is not a good idea. It's a good idea for the control. The control is more stable, it's more robust, it works well, but it's a bad idea for the utilization of the computing power that you have underneath. Ok? So it's not so good. Va bene, questa velocità va bene, si capisce? Ok? Mi alzate la mano senza problemi, rallenta e io rallento, ok? So it's a bad idea for when you want to schedule concurrent tasks and other tasks in the same application. So you typically insert a period, a wait for period here, and you try to decide the period based on the control properties of your system. I cannot, for an inverted pendulum, choose here a period of 10 seconds. Why not? Because otherwise the stick would have fallen already. Probably 1 nanosecond would be too much. It would be constantly going, okay, constantly executing. I wouldn't even have time to finish this before the next period, okay? So the size of the period should be properly selected based on the dynamics of the control system. This is an embedded system. Again, we are within something physical that interacts with the environment. There is gravity, there is the inertia of the pendulum, there is the inertia of the trolley, okay? So the way we size the period, the way we decide the period, depends on these dynamics, okay? typically, if I choose the period in the milliseconds range, probably it's a stable situation, okay? So depending, how can you imagine? So having a larger period, you will see the pendulum, okay, bouncing a lot. A short period, the equilibrium will be more stable, but there will be more computational power put to your computing system. Okay? So this is like a very simple example, but it's the basics of almost every real-time system. It always starts with control. The same applies when you have a sensing autonomous driving car. Okay? The rate at which we receive the images by the sensors, by the cameras, by the lidars. You know what is a lidar?
Yeah.
Lidar is a laser scan, okay, which essentially sends some rays at laser wavelength and measures the distance back, the time of flight of the ray and back, and it gives you a distance map, either a 2D map for cheaper LiDAR, or a 3D map for most expensive radar that you can use to create your map of the environment that you move on. Okay? In autonomous driving, we typically use LiDAR, we use radar, which are much cheaper. Essentially, all cars that you buy today have a built-in radar for collision avoidance and stuff like that. We use ultrasounds. When you try to park, the beep, beep, beep that you hear is the principal sensor is an ultrasound. Typically, you have 8 to 12 ultrasounds sparse around the newest generation of cars. And we use cameras, okay? So we use a lot of sensors, okay, to reproduce the environment that our car moves in. If I sample very often the sensors and take a lot of computation, the computing power provided by the architecture will not be sufficient. Okay? If I sample it too rarely, so if the sampling period is too large, if I sample once every second, then probably 1 second is too much for avoiding crashes and fatal accidents. Okay? So typically it's a trade-off, the one of selecting the periods. I will not give you a receipt to select the period. This is not the task, the target of this work, of this course. It will be the target of this course. Okay? So here, for us, the period is given by the physics of the control systems. We just try to make everything else. Okay? So try to put these tasks. We come with a period and a computational requirement, and we try to schedule them all together. Okay? Going on, so here is basically a scheme. You can schematize what we saw before. It's just a more compact form of what we saw before. So typically, our task will be repeated periodically. Okay. Every period will have a sample of the angle. Okay. Sampling of the sensor, computing, and actuation. Okay. This is our task. This is the simplest way you can model a task. In the real-time literature, we typically call this task Lewis-Leyland task. You don't need to remember that. Lewis-Leyland were the first one to propose such simple model back in the 70s. Okay, this is probably the main task model that we will adopt in this course, in the theoretical part. Okay, let's see how the control performances may be affected by the delay in such control tasks. Okay, so assume first the ideal world, that I can have sampling, sensing, computing, and actuation in an epsilon time. It's immediately executed. Okay, so our task is very short. Okay, we are able to do everything like in a blink of an eye. Okay, here is the dynamic of our pendulum. Okay, basically this is the angle that I measure. Okay, as long as I measure a positive angle, I will do the math and I will compute a positive feedback to give to the trolley. Okay, positive angle, positive feedback. What does a positive feedback lead to? Positive feedback will go reducing the angle. okay? We reduce the angle until we resample it again, and we may have noticed that now the angle is in the other way around. So we do a sample, we compute, and we give a negative action, a negative force, okay? We pull the trolley. So pulling it, it will increase the angle, okay? And so on. Sensing positive, okay? Sensing negative, okay? And so on, okay? Here you can see that the control is stable, okay? The pendulum is always within the devised range. Actually, the real tasks, of course, you may have guessed, are not infinitely small. The real task need to execute, so you need some time to execute, okay? So here, this is a little bit larger, okay? Not only, it can be preempted, so it is not the only task that executes in our architecture. It is not, we are dealing with concurrent systems, okay? There is not just this task. There are a bunch of other tasks that need to do other activities. So no one guarantees you, unless you have a proper scheduling algorithm, that your task will be executed all together. So in typical preemptive system, the task may start. For instance, here it samples, it starts computing, and then it gets preempted by some other tasks which execute in between, and then it resumes here, finishes the computation, restores the register, finishes the computation, and executes the actuation. Okay? So, look, you have different kinds of delay here. Pay attention. So you have a delay due by the execution time of the task, from sampling here to actuation here. You may have another delay, which is this, from the period where the task was supposed to sample until when the real samples happens. Okay? And then again, you can have again the delay between sensing and actuation. Okay? So there are multiple delays that may come to play in this setting. Let's see what happens, like the same example as before. Okay, I start. I see a positive angle. Okay, look, I do the math, and I compute, okay, you need to take a positive action that leads to a reduction in the angle. Okay, the angle starts reducing. Here I have the next sample. Okay, look, I don't sample here, but I sample with some delay. This delay causes this to go further down. Okay, so if I have a delay in the sampling, this is the sampling delay, okay, it will be sampled later on. Here, I notice that there is a negative angle, okay? Negative angle, I compute, it takes me a lot, but at the end I take the right decision, okay? I take the right decision, so I will decide to decrease this, okay? But right after deciding that I need to move the angle towards the positive side, there is the next sample. Okay, there is the next sample. Here I sample. I notice that I still have a negative one, and I still decide to take a negative action. But the negative action will be taken only here when the angle will be positive. So pulling the trolley will further increase the instability of the pendulum, and probably the pendulum will fall. Let's relook at it again. Probably at first sight it's not so obvious to you why this happens. Okay? Look at here. Here is when the wrong thing happens. So here I was negative, I decided to pull the trolley. Okay? Pulling the trolley was executed here. So it was already moving toward the positive side of my pendulum, okay? It was here, so I decided to go in this direction. But when I sample it here, and we enforce it here, I still have a negative angle. So here, when it completes, the pendulum is already here, but he thinks that the pendulum is still here. Okay? So this is the delay that I was mentioning to you. This delay is fatal for you, because you don't have now time, because the next period will be here, and the pendulum will be already full. Okay? So this is essentially due to computing delay. Okay? This is essentially due to scheduling. This is essentially due to the difference when you sample and when you're supposed to sample, as well as the difference between when you sample and when you actuate. Okay? Here you actuate based on a stale data, based on an old sense data. Okay? Does it make sense to you?
Yeah.
Yes.
Sorry. Shouldn't I have an increase in angle in the first computation?
You mean here?
Yes. Until the computation is done.
Yeah, you don't know the decision here. What was it? You know?
No.
Yeah.
After the sampling. Yes.
You mean here?
Yes.
After
Until
this, yes.
until
Here.
activation. Yes.
Yes. So the decision here depends on what was the decision before. So, for instance, here you're not yet taking a new actuation.
Okay.
Here the actuation is still the old one.
Okay.
So I didn't write it here, but probably here the actuation was to continue decreasing it. Okay. So here you read, okay, still negative. Okay, let's still continue, have a positive one, so it goes still continue. It's not a perfect line though. It's not perfect, but still it makes sense.
Okay. Thank you.
Okay. Other questions? Se qualcuno si vergogna, le faccia pure in italiano. Proviamo in inglese, ma ho voglia che parlate, insomma, più che vi vergognate. Yes.
The sensing, when the calculator take the new.
So basically, there is also here. So please, let's take it here. Okay. Here is the new task is released. Here is not the sampling. Okay. Here is just task activates. What happens at operating system level is an interrupt. That if it is an event-driven real-time operating system like the one that we are going to see here. But typically this is an interrupt, okay, maybe caused by a timer, okay? You know what happens after an interrupt. You call an interrupt service routine, okay, an interrupt handler, that what it typically does is put this task, tau I, is put in the ready queue, the queue of the ready tasks, okay? When this task is finished, it is not in this ready queue. The ready queue is the queue where the tasks are fetched to get executed. Okay, you have a queue, a coda di task pronti. A ready queue where the task is taken and put to execute. Here it finishes, so it is not in the scheduling task, in the scheduling queue. Here it is re-put again in the scheduling queue, but it is not his turn. It is not his turn to execute. Why? Because otherwise he would have executed here. So probably there was another task with higher priority, for instance, or it was non-preemptive task, okay, that executed instead. Still, the sampling did not happen here. So the sensor reading did not happen here. It will happen as soon as the task starts executing, which is where the first line of code gets executed, right? The first line of code gets executed, so this reads the sensor, and so on, okay? Basically, this wait for next period causes the task to sleep. Typically, it's a OS primitive. It's an operating system primitive that interacts with the operating system. So basically, this task is descheduled, and put in a sleeping state. So it is not in the ready queue of the operating system. Okay? Did you guys study these operating system things more or less? Okay. So basically, this is like a blocking primitive that rescheduled the task, and it will be rescheduled, resumed, rewaken up at the next period. Okay, here starts the sampling, and basically it continues until the end. Other questions? Okay, you may have guessed that the fact that we just saw tells you that we really need the system to react with precise timing constraints. The system should be responsive, especially in this kind of control environment where the period and the response time of the task may affect the pendulum stability. Again, who imposes the timing constraints? Who imposes the periods? Who imposes the deadline? It's not me, it's the dynamics of the system. Okay? The dynamics, the inertia of the pendulum, the trolley, the responsiveness of the trolley and the motor, and so on. So, in order to ensure that such timing requirements are met, you typically need an operating system support that allows you to execute the tasks when it is more convenient to you. Okay? You don't use Windows or general purpose Linux because you don't control so well the activities of the task and when they are scheduled. Okay, let me rephrase this sentence. You may use Windows or better Linux for this kind of system, but it may very well happen this effect here. So there is a period and there is some Linux primitive or bookkeeping tasks that Linux has hundreds of tasks to execute. You don't even know what is executing below your feet, you know. So with a general purpose operating system, you're never sure. There is always a variability when tasks are executed. Okay? This variability is avoided in real-time operating systems. Real-time operating systems are much more deterministic. Basically, they have a subset of functionality of Linux. You don't need all the fancy drivers or the fancy support and graphics that you have in Linux, but you have much higher reliability. For an industrial automation production line, you don't need all the fancy stuff on Linux. Okay? You need a subset of functionalities, C libraries, math libraries, and so on, that can be predictably executed with the real-time operating systems that better schedules the time when these activities go and execute. Okay? Let's make another example, so a robot control example. This was a similar trolley as before, but equipped, we are going towards autonomous driving. So let's assume a very simple robot with a camera. A camera that can pan and tilt, okay? So just to track an object, okay? So we assume two actuated wheels, okay? You can actuate the wheels. You assume two ultrasound sensors, forth and back, okay? These are the ultrasound sensors. It's a very simplified and schematized example. And you have a mobile camera, okay, which can also move itself with a small motor here, okay? And you have a wireless transceiver maybe to communicate the results of what you see. What is the goal? Our target is to follow a path based on the visual feedback that you take from the camera and the ultrasound sensor. Try to avoid obstacles and send a complete robot status every 20 milliseconds. Okay, we are going to have the chance to see better this example in the exercises that you guys are going to make with Roberto Cavicchioli in the practical part of the exam. This is just a brief introduction of it. So we will try to design it with the typical modular requirements that we mandate in our system. So it's not such an easy task. There are a lot of tasks that interact together. So I don't want to have just one loop that executes all actions overall, because maybe the ultrasound has its own sampling rate, while the camera has a different sampling rate, while the motor of the electrical motor requires maybe a tighter control, timing control. Okay? So we have different timing characteristics of the actors, of the components, of the physical components involved. Typical requirements are modularity. So this happens for everything that we are going to develop together. These are guidelines that I would like you guys always to take into account also when developing your project. So try to build your project in a modular way. So try to divide among different tasks and different components, different functions within the task. Don't write a single function with 1,000 lines. Try to write the code with good interfaces for exposing services to other modules. So this you already studied in the first bachelor program. Configurability. So we would like to adapt to different situations. Okay? We would like to extend our code without needing to restructure it altogether. Okay? Portability. So we would like our code to be applicable even to somewhat different platforms without getting crazy. predictability, this you guessed is one of the main targets of this course, and efficiency. Okay, we need to be predictable, but let's try to make the most out of the use of shared resources, computing resources, memory, and so on. Okay, so let's try not to waste memory if it is not needed. So back to modularity, which is the typical requirement that you guys heard about probably in software designing and in programming courses that you had in the bachelor course. Modularity, we will not just implement it dividing our application into different files or dividing a function into multiple functions to call and so on. There is a further modular step that we take in this course, which is concurrency. Okay? Concurrency, I know you already heard about that, but here we will really heavily and massively use it. So try to identify the physics and the timing requirements of the different components of your systems, okay, and try to configure modularly, in a modular way, the characteristics of your application. So likely, I will end up having one task for the camera, one task for the ultrasound reading, one task for the actuation of the motor, and so on. Okay, let's try to divide each task specialized to each kind of activity that it needs to perform. Okay, yeah, I mean, you need to define the data exchange with other tasks, the functionality of each task. Don't just create tasks for the sake of creating it. You need to have a very deep understanding of what the task is supposed to do. For each task, you better verify the assumption of that task and test that task. So assume, so if that task needs to read something and produce an output, so the input will have a range validity and the output will satisfy a range of validity for the next task to read. Okay? So again, we are developing a modular system, a concurrent system made of different components. One of the most frequent mistakes in concurrent programming is by not specifying correctly the communication interfaces among different tasks. Okay? These tasks are concurrent. What does it mean concurrent? They concur, they work together to achieve the same one common goal. Okay? So these tasks are not separated. They, at some point, either they have a shared object or a shared memory, or they communicate between each other in a distributed paradigm whatsoever. So if it is a concurrent system, these tasks need to communicate, to synchronize, to do something together. Okay? So you will have to properly define the boundaries of the activities of each of these tasks. And of course, the timing requirement, the period, the deadline, if there is a jitter. Jitter is what I saw before, what I showed you before. Okay, the jitter is basically the variation, the variability in the response time. So here it finishes here, while here it finishes here. Or here it starts right away, and here it starts with a delay. This variability that you have in the starting and finishing time, it's called jitter. Okay, jitter. Of course, you have guessed that jitter affects the control performances. Okay, control systems do not like jitter. Okay, because it means that sometimes I control the pendulum like this, but other times I let it go like this. So it's not a stable control. It's better to have a fixed jitter and a higher delay than having like sometimes, most of the time, a small delay, but sometimes a very large jitter. Okay. Okay, so this is the control view of the autonomous small car that we schematized before. So let's try to understand together the components. Again, modularity. Okay, what are the tasks involved here? Okay, we have a camera. Okay, it starts from the camera. What do we need from the camera? We need some kind of feature extraction. Okay, if you are going to take some course on image processing, which we have in this master degree, typically they will show you many different techniques from which you can take a JPEG or a video or whatever compression that you have and take some information about what it sees, like the distance of an object or, I don't know, the contour of an image and so on. Then If you have a feature extraction, you may try to recognize an object. That's what we do in our cars. So we decide whether an object is a car, or is a person, is a bike, or is whatsoever. That feedback can go to the vision-based navigation. If I know where are the objects, I can try to avoid hitting on them. Okay? When I have an understanding of my environment, there will be a functionality that will guide me in a safe path, try to avoid the obstacles that I encounter. So this obstacle avoidance eventually will lead to the real vehicle control. Okay, so here maybe I compute a path. Here I decide what kind of signal to send to the electrical motors to follow this path. Again, this is also another control problem. Okay, I can decide the path, but the decision to take this path are regulated by the inputs that I give to the electronic motor, to the electrical motors. If I take one decision every second, if my curve should be this, and I will take an action every second, the inertia will cause me to do like this, not following very smoothly, right? Instead, if I take very frequent control action, I will smoothly follow the path, but I will waste a lot of computing bandwidth. Okay? Again, it's again the same problem. Everywhere here you have the same problem. So, vehicle control and the motor control. Let's also try to think about the timing dynamics of the involved agents. The motor control typically has, I told you, a very short control loop. So the electric motor needs to have a very quick, fast feedback. Okay? If you need to change slightly, you can imagine, this is hypothetical, a dynamics of about 1 millisecond. So every millisecond you would like to have a new sample, a new target current to send to the electric motors. Okay? This is the tightest period, the smallest period in our application. Like the decision of the path to follow can be slightly larger, 5 milliseconds. Obstacle avoidance can be 10 milliseconds. These are just random numbers. Okay? It can even be like much larger than that. Okay? Typically, the dynamic of the system allows you to take a larger period here. So in 10 milliseconds, it's very tiny the path that a robot can take. While the sampling rate here, it's around 100 milliseconds. What does it mean, 100 milliseconds here? It means that my camera samples images at 10 hertz. Okay, 10 hertz is 100 milliseconds. So these are the typical sampling rate. We have cameras of about 60 hertz. So in this case, that would be lower than 100 milliseconds. But that's a convenient thing to think about. 20 milliseconds. This is a 50 hertz camera. So here you have the tracking. So the tracking means now I would like to actuate the camera motors to track an object. Okay. So again, these are electric motors that require 1 millisecond, but I have the visual tracking system that requires a quicker loop than 100 milliseconds or 20 milliseconds. Okay, just examples. Okay. Ultrasounds, where they are here, ultrasound, again, the ultrasound will give me some kind of understanding that can complement the information I have from the camera. So the process of trying to understand obstacle and environment by multiple sensors, in this case cameras and ultrasounds, is typically called sensor fusion. Okay, sensor fusion is not a part of this course, but there are techniques to do sensor fusion involving some control algorithm, Kalman filter, and so on. Okay, so but these are typical control examples to bring influence them. That was the control view. How is the software view? We are not control guys, we are software guys. Okay, so we receive the control specification by the control guys, and we map them to tasks. So, how do tasks communicate among each other? Tasks communicate through memory. Okay, so a task writes to memory. The other one maybe has a different period, will eventually read that, and compute and write to another buffer, which will be read by someone else, and so on. Okay? This is a simplified scheme in which tasks are circles and memory buffers are squares, rectangles. Okay? So the feature extraction task from my camera will extract the feature and write them in shared memory. Okay? Two tasks will then read from this buffer here. So the object recognition and the visual tracking with their period, with their respective period, this one had 100 milliseconds, this one had 20 milliseconds, will read this buffer. This is a shared buffer. We will eventually need to synchronize the reading from this buffer. If multiple tasks try to write and read simultaneously the same buffer, there are race conditions. There may be consistency problem on the read or written data. Were you aware of that? Did you study that in operating system? Okay, more or less, okay. Then, object recognition has its own buffer, visual base, writes to another buffer. So this, you can see, this is like our task view. We will have a lot of circles that will be scheduled to the same processor, and everyone has its own memory buffer in the shared memory. Okay? We will need to schedule this, everything together, so that the timing requirements are met. Okay? This we said already. So, scheduling all those tasks that we saw before requires having real-time systems. So not only taking care of the correctness of the functional behavior, but also taking a look at when the results are computed, what the timing is. Okay? How is this interaction between sensing from the environment and actuating, modifying my position in the environment? How is this delta? Okay? How does this delta affect my control performances? Okay? Real time means that the real part means that the system time shall be synchronized with the environment time. Okay? We do not have a virtual time here. We really need to be synchronized with the real time. So what does a real-time operating system do with respect to a general purpose operating system? So real-time operating system manages concurrency, also an operating system does that. It activates typically periodic tasks at periodic time. Okay? This is a typical task of a real-time operating system. It has timer to trigger periodic events. Okay? Also in general purpose operating system you have timers and possibility to activate them. Only the timing is more precise on an RTOS. Okay? RTOS. It can better decide the execution order of the real-time tasks. Again, also general purpose operating system does, but its scheduling algorithms are mostly aiming at improving average performances. The real-time operating system scheduling mechanisms are aimed at addressing worst-case performances, okay? At being predictable, avoiding worst-case delays, and so on. Solving possible timing conflicts when accessing shared resources. Okay? I told you before, if we have three tasks that read and write to the same buffer, there will be some kind of locking mechanism, some kind of mutex, some kind of semaphore. Okay? Things that you saw already, but that we will see in more depth in this course. Also, trying to acquire the locks to protect a shared resource it's an operation that may lead to a delay as well. What if I'm trying to enter a semaphore which is currently held by a different task? Okay, I will need to wait until that task releases the semaphore or the mutex. We are going to see that better. And manage asynchronous activities, so interrupt handling. Okay, an RTOS is very good at handling interrupts fast and quickly, without needing to save all kinds of registers in the world. Okay, it will basically do its activity in a quick, smart, efficient, and predictable way. Okay, so a typical misconception about real-time systems, I already told you in the first class. So why don't just we use a faster and more powerful computing unit to allow me to better schedule a real-time system that did not meet its timing requirements? Well, a real-time system is not a fast system. You can have a real-time system that runs on a smaller, on a weaker, on a processor which has a smaller frequency. Okay, you are not much concerned about average responsivity. You are concerned about being predictable. So the objective of a system, of a general purpose system, of my laptop, is being fast, is to minimize average. Okay? But the real-time system tries to guarantee not the average response time, but the individual performance in the worst case of each of the tasks. Okay, if I have 8 tasks, I would like that all 8 of them meet their requirements, which are different from task to tasks. Okay? So, we said that testing is not sufficient to have provable guarantees, to have analytical grounds about the task not missing a deadline. Okay, testing is not sufficient. We should provide scheduling support that by design avoids bad situations, critical situations, and we need to couple it with a tight timing and schedulability analysis that assures all of the tasks that you handle not to execute beyond their deadlines. The typical example, yes, it was in Gustavo's book, so you don't trust the average when you need to guarantee the worst case, okay? So a typical example is a guy that crosses a river, and that guy dies drowning, but the river was just 10 inches deep on average, okay? Average does not guarantee you being safe in that case. If there is a sudden, very deep, pit while crossing the river, okay? We really need to avoid this deep pit, these deep holes when you cross our real-time river. So, what are the causes of increasing the delay in our architecture? What can be the factor behind that deep hole when you cross the river? What can augment, what can increase the response time of your system beyond what you typically expect? There are multiple factors in a computing systems. Architectural factors include caches, the memory hierarchy. You know what a cache is, right? So caches, in this system here, this is an Intel quad core. You typically have a level 1 cache close to each of the core. You have an L02 cache shared by all the cores, and you have an L03 cache with a lot of replacement policies, a lot of consistency policies, a lot of optimization policies, out-of-order execution, speculative fetching, and so on. So you may execute your program 10 times and have 10 different timings out of it. Okay? Caches, pipelining. You know that the processor is made of a pipeline. Typically, you have typical pipelines is a fetch an instruction, decode the instruction, execute the arithmetic logic, execute the floating point, write the instruction, and so on. And you typically execute multiple pipelines. You typically execute multiple instructions altogether, right? You may have hyper-threading. You may have a lot of things that are used in general purpose architecture to optimize performances, okay? While one instruction is waiting for the data to be fetched, I schedule the next instruction as long as there is not a data dependency between them, and then I go to the next one, and then this becomes ready, and then I schedule it, and so on. There are a lot of hardware mechanisms which aim at improving the average performances of these kind of architectures. DMA, interrupts, again, I try to execute a task, but then an interrupt comes, and that task is preempted, and another interrupt comes, and that task is preempted, and so on. DMA are engines that are used to transfer memories, to transfer memory locations from the main memory to the local cache or closer to the processors. So all these architectural, unpredictable factors. Second thing, operating system. Again, if you don't have a real-time operating system, the typical operating systems are designed to maximize average performance. So you have schedulers that try to minimize the average response time. You will have some kind of synchronization mechanism that try to minimize the response time. You have communication mechanisms that do not take into account predictability. Then programming language. Okay, we didn't learn C or C++ with the concept of timing in mind. Okay, when we wrote our program, we never thought about the timing of it. Did you? I didn't. Right? So when you write a program, you just focus on the functional requirements. You don't think about the timing of it, right? But then you execute it, and the timing is noticeable sometimes. Okay. Design methodologies. So we do not know well how to write codes, try to avoid that bad timing delays arise, okay? So trying to avoid all these kind of OS and application features, unpredictable features, traditional real-time systems designers were writing their application using low-level coding. So the typical application 10, 20 years ago were written right away in assembly. Okay, I want to really know what's happening below my feet. I take an architecture, I study the assembly, okay, and I write an assembly program, because then I know what's happening every time I do it. I do not delegate the compiler to rephrase the code or take some action that I don't control. So initial real-time systems were using heavily the assembly programming. The timing was through dedicated timers. So every task has its own dedicated timer that needed to fire at exactly that moment in order for that activity to be executed exactly then. A lot of control through driver programming and a lot of handmade priority manipulation. When you realize that some task misses a deadline, then try to rephrase things and try to accommodate it. So this was a wrong approach, because it requires a lot of low-level programming, a lot of low-level insights. And once you fix a problem and you try to reconfigure your system, then you need to redesign it completely. So this is not a good way to go. Okay? This is not what we will try to do. Because this programming, tedious programming, strongly requires a programmer to understand a specific architecture. If you change the architecture, he will never be able to reapply what he wrote until now. It is difficult for someone else to understand what the first one wrote. Okay? If you work in teams, which is basically the case when you work in industry, everyone should be aware that his code will be read by someone else. Okay? So you need to write in an understandable way. It's difficult to maintain millions of lines of code of assembly code. Okay? You probably already know that when the compiler translates C instructions, they map to tens or 20 or 30 instructions of assembly code. So understanding may take more than rewriting your code. Okay? So that's the basic reason why when you move to a different architecture, you throw away your real-time code you had before and you restart writing it, because trying to understand what someone else did or what you did a few years ago does not make sense. It's difficult to verify timing constraints in such no modular architecture, and there is a significantly low reliability. So it's difficult to detect failures and understand what the code is doing. So the bottom line of this introduction is that the tests, while necessary, do not allow you a full verification of your system. So we must achieve predictability throughout the whole computing stack, throughout the whole computing levels, starting from architecture to middleware, operating system, application. We really need to take care of all these levels if we want to make sure of when an application does what. And again, always think the worst. Always apply the Murphy's law, okay? Always make pessimistic assumption about what may happen, okay? Are there questions about this initial motivating session that we did together? Otherwise, I will move to okay. So don't worry, I will finish up a little bit earlier today because it's 5 o'clock already, so probably you're tired. I can see you, I'm tired. So let's try to finish around 5:30. Is that okay? So another half an hour, and then we will see each other on Friday. So this is, I would like to start like a summary of some of the things that you already saw in your bachelor studies, okay? So the first slides probably will be boring for you. These are things that you already know. I would just like to make sure that you remember it, okay? Let's just try to get back on what is a process, how is your architecture made, what is a thread, and so on, okay? So a fundamental concept in a real-time in an operating system is the concept of process, the notion of process. What is a process? It's an executing program. It's not the program, it's not the code. The process is the instance of that code that executes, okay? This is a process. An operating system can execute multiple processes, of course, at the same time, okay? I can have the same code and multiple processes of that same code. I can have different codes whatsoever, okay? The action of executing, or the property of executing multiple processes at the same time is called concurrency, okay? Pay attention to what do I mean with at the same time. It doesn't necessarily mean that at this clock instant there are 6 processes making progress, okay? It basically means that there may be multiple processes which are pending for executing, okay? The architecture that allow you to have multiple processes making progress are multi-core architecture, are parallel architecture, okay? If you have 2 cores, you can have 2 processes progressing, okay? If you have 1 core, only 1 process at a time will progress, okay? Still, you may have a concurrent application. You may have 10 tasks which are ready. Some of them started executing but have been preempted. Another one arrived but did not started yet. Another one completed. Another one is executing, and so on, okay? So there are multiple tasks ready to execute, that want to execute, that are waiting for some precedence constraints, and so on. And they all collaborate to achieve one or more common goals. This is called concurrency, okay? You don't need a multi-core architecture to have concurrencies, okay? You need multiple processes. The difference is between concurrency and parallelism, okay? So when a process executes, a process typically goes through states, through different states, okay? So what is a state of a process? So this is a deterministic architecture. So the state of a process typically is given by the state of the memory and of the registers, okay? So if my code has some kind of global variable, local variable, and so on, if I freeze the clock at some point, I take a look at those variables. These are the state of my process. The program counter is 125. The A variable is an integer which is 4, okay, and so on. This is the state of my process. So this is a simple program that I never remember by heart, but it's a simple way to compute the greatest common divisor with 2 lines of code between 2 integer numbers, okay? This is while A is different than B, compute if A is less than B, then assign to B, B minus A. Okay? Otherwise, assign to A, I minus B. Okay? If you iterate, at the end, you have the greatest common divisor between these two integer numbers. Okay? So every time the program is launched, I can launch this program 10 times. I will have then 10 instances, 10 processes of this program. Okay? So the typical step, if I give A 21 and B 15, what you expect is that from step to step, the program will evolve, okay, until the greatest common divisor is reached. Okay? So this is a state, this is another state, this is another state, and so on. So the state of the variable determines the state of the process. Okay? Besides the variables, there is the operating system state of that process. So the operating system needs to label each process according to the state it is undergoing. For instance, a process may be ready to execute but not executing. A process may be executing. A process may be blocked, waiting for someone, for a semaphore, for a lock, for a mutex that is held by a different process. Okay? A process may be terminated. Okay? So let's see the nomenclature of the states of a typical OS process. Starting is when the process is being created. Okay? For instance, a new period arrives, I'm starting to create the process. Ready, okay, I created the process. Okay? The period just arrived, the inter-server routine created the process, I inserted it in the ready queue. The queue where the scheduler will fetch the processes to execute. Okay? Executing, you know what this means. Blocked, for instance, this process requires semaphore A. Semaphore A has been granted to a different task, okay? So this process is blocked. This was executing, okay, is descheduled typically, and someone else is executed instead. This is blocked, waiting on a condition, or on a shared resource, or on a synchronization event, or on you name it. Terminating when the process is about to terminate. And typically, a process during his life goes along all these states. This is like the typical state chart where you just start once, okay? There is no way back here, so you start, okay? Then task is ready. Task ready can either go, the task ready can either stay ready or eventually go to the running state, okay? This process here, this state change is called dispatch, or the process is scheduled for execution, okay? This is creation, the process is in the ready queue, and this is scheduled to execute. It is dispatched to the processor. Now it is running. When the process is running, it can take different paths, okay? So when it finishes execution, basically it terminates, okay? I finished all the code that I needed to write. I end at the end of my task and I terminate, okay? Or there can be a semaphore that I need to acquire, but it's held by someone else. Then I enter in the blocking queue. I enter the blocked state, okay? This process is typically called, this transition is typically called the suspension or wait on condition, okay? Typically, when a process runs from here to here, we say the process is suspended, okay? It can be an active suspension or a blocking suspension. So active means that the process keeps waiting for that resource to be available, to become available, or the process is blocked instead, is descheduled, and now the core is used for someone else, okay? It can be an active polling or a blocking primitive. Instead, if when the process is running, a higher priority task arrives and preempts my running process, the running process goes back to the ready queue. This arrow here, so when a process which is running, which is not blocked and did not terminate, is preempted by someone else, is called preemption. Okay? When a running process, okay, relinquishes the processor to schedule someone else, while before finishing its execution. So this is called preemption. Is it clear? Shall I repeat? I don't see many of you nodding. È tutto chiaro? Così temi di no, eh? Sì? Ok. La preemption è quando appunto il processo non è ancora finito, no? Viene interrotto da qualcun altro, ok? Dopo, quando lui potrà ritornare a eseguire, no? Una resumption, e dopo continua tutto. Okay, so process queues. So what is the ready queue that I named before, that I told you before? Here is a very simple example of how it can be made. So when a new task arrives, so it's created, it is inserted in the ready queue. It's just a queue. It can be, I don't know, a queue which is stored in memory. Here you have maybe the task index, the indexes of the tasks that are ready to execute. Okay? I can sort this queue, I can order this queue according to any scheduling algorithm that I want. So the way in which I order this queue, the way in which I sort this queue, affects the way tasks are taken and executed on the CPU. If I use here a priority-based ordering, so I will put in the head of the queue the highest priority task, and in the tail of the queue the lowest priority one, then what I implement is a fixed priority scheduling algorithm. If I instead put here the first one that came, and at the end the last one that came, I implemented here a first in, first out scheduling algorithm. If I put here a deadline-based scheduler, for instance, here is the task that have the most imminent, the earliest deadline, and here is the one that has the latest deadline. I implemented here an earliest deadline first scheduling algorithm. Okay? So the way I decide to sort these tasks is the scheduling algorithm. Affects the way tasks are taken and dispatched to the processor. Okay? It can be preemptive, non-preemptive, limited preemptive, or so on. So what is a preemption? A preemption happens when, okay, I'm executing a task here. Okay? I'm using a fixed priority scheduler. I'm executing a task here. Now a very high priority task arrives. It is inserted in the queue. It preempts the one that was executed, which is scheduled back in the ready queue. And now I'm executing the highest priority one instead. Okay? This is the process of preemption. Okay? If instead of the task being preempted, is the task itself that reaches, for instance, a semaphore waiting primitive, and it is not able to enter that critical section, then it is blocked, and typically you put the blocked tasks in a semaphore-based blocking queue. Okay? When will be the task unblocked? When one of the executing tasks will release the semaphore, okay? So it will cause a wake up of this guy here, which will return back to the ready queue. Okay? This is the way the operating systems are made. If you have multi-cores, which is the state of the art today, you don't have just a CPU, but you have multiple CPU. So instead of taking just the first one in this queue to get fetched and executed, you take the first three ones which are fetched to the relative cores. Okay? Everything depends on the scheduling algorithm here. You can even have core-based queues. You can statically assign tasks to CPU and have each CPU having its own queue. If you take a look at the Linux scheduler, you have an even further option. You have affinities. You can decide that a task may just execute here or here, but not in this one. Okay? So you typically have per CPU queues, okay, which are sorted according to any kind of scheduling algorithm. Okay? Oh, this is the same example for one core, but multiple blocking queue. I would like just not to have just one queue for all blocked tasks. I would like to divide the blocked tasks based on the condition that they're waiting to happen for their unblocking to take place. Okay? For instance, this is the blocking queue for semaphore 1. This is for semaphore 2. This is for mutex 3. Okay? What do we bring in the operating system to accounting for the process activities? So we have a data structure in the operating system which is called process control block. The process control block contains all data that are related to the process. So the process control blocks are stored typically in a table in the privileged memory region of the operating system. Okay, so you have a table with multiple pointers to multiple process control blocks. Okay, so this is, for instance, one process that has these process control blocks here. Okay, what do we have in the process control block? It depends. It is OS dependent. It depends on the operating system that you are using. It can really vary heavily. Okay, you can have the process identifier, the PID. Okay, it's a unique identifier of the process that is that we are dealing with it here. Okay, you can have the ID of the parent process, so the process that created this process. Okay, you can have the user identifier. Who is the user that created this process? Who this process belongs to? You can have a state of the registers that are related to the process itself. So this process has a control register, has an instruction pointer that reached that point, has a stack pointer. You know, you studied that, right, in the computer architecture. You have other registers that the OS may decide to keep track about the process. You have the state here that we saw before: ready, running, blocked, terminating, idle, whatsoever. You have the priority. You may have the priority in a priority-based OS. You may even take track of the time left until the deadline. Okay, and whatever you name it. Okay, it's not a fixed data structure. It depends on the OS you're using. Okay, process control block. Why do we use what do we use the PCB for? The PCB is used within the operating system for a number of components. Of course, you may have guessed, if I have the priority of the time to deadline, and the state, I can use the PCB information for the scheduler. Okay? The scheduler may decide which process to execute. If I have a scheduler, I read the priority of that process at the right, and I decide how to schedule it in the ready queue. Virtual memory, virtual file system, and interrupt handler. So you may use all of these access information of the PCB. Only the operating system accesses the PCB. Okay, you cannot read it. Okay, unless you pass by means of primitives, OS primitives. Exactly, only by using appropriate system calls. How is the memory layout of the process? So the PCB describes synthetically some high-level information of the process. But how is the real memory of the process made? So typically you have each process, for each process, a dedicated memory which is divided into different segments. Okay? You have the process code. This is the code that you execute of the process, right? Your assembly code, your binary code that the process should execute. You have initialized data. Okay, these are data initialized by the loader. It may vary from OS to OS. You may have data which are not initialized by the loader. Okay, the BSS section. Did you study these segments in operating systems? No. You may have heard of them, right? But you didn't study them, right? So this is the typical structure that you have for the memory of a process. Then you have the stack. You know what the stack is, right? So when you do a push or pop, you call a function, then the stack increases. When the function finishes, the stack increases. It increases only in one direction, okay? And when you pop, it decreases. Then you have another memory region, which is the dynamic memory, so that you typically allocate through by means of malloc, new, and so on, okay? As soon as you need them, you allocate there. And then you have other data, okay? In some systems, the PCB is in the other data section. Okay? It was like this in Linux, I'm not sure if it still is here. Okay, so each process has this memory layout. Okay, a different process has a different memory layout. Typically, you do not allow, an OS does not allow one process to access the memory region of a different process. Okay, these are memory isolated. Okay, this process, if you know what is the error, the warning that you receive by the OS when you try to access a different segment? Segmentation fault. Okay? This is nothing else than trying to access a different segment than the one that has been assigned to your process. Okay? Segmentation fault. How many times you try to program your programs and received a segmentation fault? For instance, because you accessed a null pointer. Why segmentation fault? Because memory region 0 is not the domain of the process you are executing, okay? It's typically reserved to the operating system. So, better, each process has its own memory space, but part of it is private to the process. Only that process can access it. Part of it can be shared by other processes. For instance, two processes of the same program, so the same code, may share the text file. Okay? May share the text file. Okay? These are two instances of the same program. Also, two processes communicating by shared memory may share a portion of the data segment. Okay? If properly set in this way, two processes communicating by shared memory can share some kind of the data region, the data segment. Okay, this is what we just said. So one process tries to access memory location of the space, then you have a thread by the processor, okay, an exception raised, and the process is terminated with the segmentation fault message, right? It's also related to the virtual memory, right? You know what virtual memory is, right? So every modern processor supports two modes of operation. The typical way we run our program is in user mode. Then you have another mode which is supervisor. A bit in the control register tells you which mode you are in now. So the processor may be running in user mode or may be running in supervisor mode. If you check the related bit in the control register, you understand what kind of mode you are running. Typically, the operating system runs in supervisor mode, okay, in a privileged mode. Okay, the OS typically needs to freely operate in every part of your architecture. Okay, if it is the only operating system executed there. If you have an hypervisor, this is not the case. User code runs in user mode. When you move from user to supervisor or vice versa, the operation is called mode switch. Okay? When you go from user to SU or SU to user. The mode switch may happen by means of interrupts of trap or traps. So these are maybe related to faults or some kind of events that take place. So in this case, typically before calling the interrupt handler, when an interrupt arrives, okay, there is an interrupt, for instance, by a device or by someone else. It's not the user mode that deals with it. Typically, I make a mode switch. I make a mode switch to a supervisor mode. which disables the interrupt. So an interrupts come, I move to supervisor, interrupts are disabled because I would like first to deal with the one that just came, okay? I serve it, okay? And I move back to user mode, re-enabling the interrupts, okay? Did you study that in operating system, right? If you recall, this is the way they work. Or a mode switch may happen with a special instruction, okay? It was INT in the x86, the software interrupt that allowed you to pass to this new mode. Okay, with this we don't exactly need it. This is some kind of in older architecture. It was some older code that was used in x86 systems. But again, you had a software interrupt that caused you to move to supervisor mode, save the context, execute the function open, restore the context, okay, and return from supervisor mode. What is that? This is a system call. This is an open, okay? This is a system call. This is not a library that of code that you executed. This is a call to operating system functionalities, okay? This needs to access the file system which is managed by the operating system. It is not a library that you wrote in C for your code, okay? So when you call an open, you will not execute it in the user mode. It will be the operating system that executes it on your behalf, okay? Whenever you do an open or a close or a read or whatsoever, these are system calls. Okay? These are primitives, operating system primitives. So when you call them, whatever happens is that the program moves to supervisor mode. You have all these context switch overhead. So there is an overhead, there is a delay implied in calling system primitives. Because you need to save the context, okay? Why do you need to save the context? Because we said that if you remain in user space, you have your memory region. Now you go to a different region. This is the operating system that executes, okay? So whatever was in your stack, the stack pointer, instruction pointer, program counter, control register, everything, you need to save it in memory for being restored when you return back from this call. It will not be your program executing, it will be the operating system using its own program counter, register, whatsoever, okay? So you really need to save the context, then the operating system will execute the function read, open, close, whatever, and then it will restore the context and move back to user mode, okay? So this is a typical process. So save register and everything, context, okay, local variables if you have any, and then restore them at the end of this operation. Yeah, note that the open system call, this system call is potentially blocking. So it is a potential preemption point for this process, okay? It's a scheduling point. It may happen that the process is blocked. We have a process which another process is executed instead, okay? This is everything that can happen in a general purpose operating system, right? So when does a process switch may happen? When a high priority task arrives, we see that that may cause a preemption. It is a preemptible operating system. This indeed may happen. When a process blocks on some condition, okay, we already said that, right? I want a semaphore, not available, I block, okay? And someone else executes on my instead of. In time-sharing system, it's an even different approach. In time-sharing system, you typically have a synchronized clock that executes, that decides who executes at each period. Okay? From here to here, it's a task to execute. Then it's another one. Then it's a third one. Then it's a fourth, and so on. So in time-sharing system, it can be an interrupt that interrupts the process and executes. We schedule that process and execute someone else. Okay? This is a time-sharing system. So since we would like to restore the process later, this is the very reason why we need to save its state. Okay? I'm insisting in this because I would like to you guys getting aware about the overhead implied by a context switch, by a process switch. Okay? When we change process, there is a context switch implied. There is an overhead that you need to pay. It implies saving something and restoring back. Okay? This may affect your timing guarantees. One of the main metrics that we use to assess the validity of a real-time operating system is the context switch overhead and the interrupt service latency. Okay? So how much does it take from a process to get interrupted and execute a different one instead? And how much does it take from an interrupt arriving and the first instruction of the interrupt handling routine to execute? Okay? These are typical overhead that you measure in a real-time operating system. So every operating system has an exec pointer. Basically, if in a single core system, there is just one process executing. So the exec pointer is the pointer to the process that is executing. Of course, the status of the executing process, it will be running. When a process switch occurs, the exec process may become either blocked or ready. Okay? Whenever a process is descheduled, there is a scheduling decision implied. So the scheduler is called, and the scheduler will decide which process to execute next. Okay, this is again a system call that causes a process switch. We saw it before already, so see it again. We change to supervisor mode. Here we see it in more detail. We change to supervisor mode. We save the context in the process control block of the executing task, okay, including the stack pointer. Okay, we save everything of the executing task. The process changes status and goes into blocking mode, okay, because now the process is blocked, and we call the scheduler. So the scheduler basically moves the executing task into the blocking queue and selects someone else to execute. Now the exec pointer points to the new process, okay, and then you have the restoring back all the things that you saved before, okay. You may see it in a more dynamic way here. So you have two processes. This guy is executing, okay, while this one is blocked, okay. So here you see that this one is using all the register around, and this one has some register saved in memory in his stack. Okay, so the preempted or blocked process, the one that is not executing, started executing before, so we needed to save the state where it arrived. Why? Because we don't want to throw away what it computed before, right? So we saved everything, okay, including the IP, control register, parameters, whatsoever, okay? Then what happens? When we want to do a process switch, so we would like this guy to get preempted and execute this instead. So we start saving parameters of the executing process, okay, the parameters of the executing process, at least the one that will be polluted by the context switch. Again, because we would like to restore it when it will be timed. We will save the control register, okay, keeping track of the current state of the process that was executing. We will save the instruction pointer. We would like to know where we arrived in the execution of the code of that process, right? So we need to save the instruction pointer where it pointed to at this time. Okay, and all the registers, okay, possibly in the process control block. Okay, we saved everything. We saved the state of the process to be preempted. And now we move to blocking state. Okay, now it's blocked. And now we start executing the other one, okay, popping all the register and the things that have been saved in the stack. Okay? You can guess that this implies some overhead, right? Okay, this is only an example. Every operating system has variation on this theme. And register may be saved in the stack or in the PCB or whatever. You can try it if you want. You can take a look at the kernels of Windows, not all, Linux or FreeBSD or maybe some real-time operating systems that we will see together along this course. Okay? I would say that it's enough for today. Okay? So from next time we will continue this survey on processes, threads, okay, before introducing the synchronization primitives and private semaphore that we're going to see again.